Yeah, and I mean, yeah, let's keep it informal. So whenever we have questions, I mean, we might just interrupt you, unless you prefer us to wait until the end.
Maybe I can just say when a question will be answered later.
Okay,
yeah.
Sounds good. Sounds good. I don't know. Like, I think Bertrand, you've met Francesco at ICML, right? I think Tao hasn't met him before. I mean, we met Francesco this year at ICML and had wonderful discussions about uncertainty estimation. And then I ran into him again at ECCV, where he was presenting this work. And I thought it's probably interesting for people who usually join this reading group as well. So yeah, please go ahead.
Okay. Hi, I'm Francesco Pinto, and I'm a PhD student at the Torr Vision group in University of Oxford. And as Yanis just said, I will present the paper, An Impartial Take to the CNN versus Transformers Robustness Contests. What's the overall story of the paper, and what we are concerned about is that there is a part of the literature that states that transformers are more robust and reliable of CNNs, and also they usually blame this on the self-attention mechanism they use. And actually, this paper started exactly from this literature, and we wanted to understand what was so special about self-attention that made transformers so robust. And then we started digging a bit deeper into the analysis that were done, and we sort of thought that there was something off, and we didn't agree with the narrative. So this paper sort of questions the idea that transformers are more robust and reliable than CNNs. Now, I will make a few preliminaries just in case some people may not be familiar with uncertainty estimation in the setting of classification, but they will be very quick. We all know that neural networks can do classification very well, and they have state-of-the-art performance. However, they can be extremely confident even when they make wrong predictions, or they can also assign class labels even when the input does not relate to the known class labels. So in this case, we talk about out-of-distribution data, or more probably open set data, because usually people talk about closed word assumption, open word assumption, but let's not go into the detail of this. Another problem with these classifiers is that when they're exposed to unusual inputs, they can be wrong, and be wrong with high confidence, or they could not even recognize what they're seeing. For instance, this cat is a very peculiar type of cat, but still we recognize it as a cat. Now, in this work, in this presentation, we will refer to robustness and reliability in these terms. In terms of robustness, we're talking about covariate shift. So when the distribution of the inputs differs from the one of the training sets, but the set of labels remains unchanged. And in this case, we would like to have an accuracy that doesn't drop particularly badly in this case. About reliability, we will mostly refer to the ability to discriminate between in-distribution and out-of-distribution samples. We will talk about calibration very quickly. Calibration means assigning a frequentist meaning to the probability that comes out of a softmax. So we want to match the accuracy and the confidence of a classifier. If a set of predictions has 80% confidence, then we want the classifier to be 80% accurate on that set of predictions. Then we will also talk about the ability of distinguishing misclassified samples from correctly classified ones. Okay, this is just to give a very broad overview of what we're going to refer to as reliability. Now, as Yanis asked me to perform a short literature review about the existing transformers literature, I've prepared a few slides in which we discuss and cite some parts of the literature where this kind of statements are made. In general, the literature says transformers are more robust and reliable. In particular, there is this paper that came out at NeurIPS 2021. And what they do is they perform a series of experiments about covariate shifts. And what they observe is that comparing the performance of a ResNet 50 with a transformer called VITS, They observe that the ITS performs much better under covariate shift. And what they do is they try to align the training techniques used for ResNets and DET, and they observe it is not possible to bridge the gap between ResNet 50 and DET. And for this reason, they conjecture or at least suggest that the self-attention is the reason why this gap cannot be bridged by just aligning the training procedures between the two. And also they perform some experiments with hybrid architectures, and since they see that the performance is sort of intermediate between having convolutional biases and having self-attention biases, they argue that it might be due to self-attention. Of course, a big limitation of this work is that it only considers very small models, the ITS, the IT mini, it only considers ResNet 50, 18101. And also it might be questionable whether you should align the training procedures of the various models, because it is not guaranteed that a training procedure that works for a certain type of model also applies well to the other one. And these things are very model specific, and changing inductive biases can really have an impact on this. Another paper that was also published at a big conference, in this case CVPR 2022, performed an extensive analysis about the covariate shift performance, and it still compares transformers with convolutional neural networks. First of all, I would like to observe that many times when these papers talk about convolutional neural networks, they mostly talk about one type of convolutional neural network, which is the BIT, which was from Google, if I'm not wrong, a big transfer. This paper was pretty popular. And what they do is comparing VIT or DIT against BIT. As you can see, I reported a few citations. In general, there are statements about the bias of transformers to shape so that it makes so that it generalizes better when there are texture shifts, or it is more reliant on the foreground feature of an image rather than relying.
I think I have some
background, and more explicitly, we will see even more explicitly in other papers. Yeah.
I think we heard the last 10 seconds. We missed the last 10 seconds because you were gone.
Okay, sorry, I didn't even notice it. Did you hear about DIT and BIT?
Yeah, we heard that.
Okay. Basically, the statements they make are about the ability of VITs to be more oriented towards the shape rather than the texture of an object. So when there is a shift in the texture, they generalize better. They also make statements about the fact they tend to rely on the background less than CNNs. And as usual, there is either a weak reference to the self-attention mechanism, or as we will see in the next slides, as other papers have even stronger references to the self-attention mechanism being the cause of this thing. This paper is about calibration instead, and they perform a quite extensive analysis of several.
Francesco, I think Bertrand has a question.
Yeah.
Yes, I might have a question. So just, it's not clear to me. So how do they support these statements in these papers? So do they do some experiments where they just change the texture and observe that there is no impact, or?
So in the first paper I presented, they do this experiment where they insert attentional components inside an architecture. And for this reason, since they observe intermediate performance between a fully convolutional model and the model with self-attention only, they justify it this way. In these two papers, they don't really provide a strong support. They just mention it vaguely. In this paper, they have a full section about this, and they do some experiments, but these experiments are also a bit questionable sometimes, or at least they can be discussed. But yeah, I will cover this kind of experiments later. Actually, probably I can present this one before. Basically, in this paper, it is argued that transformers are robust learners. In particular, they do experiments on out-of-distribution detection and covariate shift. They come to the conclusion that transformers are better from this point of view. They present several experiments about the fact that self-attention is supposed to help. In particular, they talk about the fact that if you inject some spurious features doing, for instance, some high-frequency Fourier transforms, Fourier noise, you inject it in the features and you train models on them, transformers tend to pick it less. But as we will see later on in the presentation, we also did some experiments, and maybe transformers are less keen on that type of bias, but they can also pick spurious features when they are simple, and they don't avoid this kind of bias to simple features. They also do some other experiments about combining convolutional parts and attention parts, and as seen before, they obtain mixed results. So they say, okay, attention is an important component of robustness and reliability. So yes, sometimes these statements are supported by experiments, but generally they are just ablation experiments, and they don't tend to be conclusive, even though the message that passes through is, oh, okay, it's self-attention. Because obviously self-attention is the most prominent component of a transformer. It's the component you need to understand in order to understand the difference between a transformer and a CNN. And it's a bit natural to blame it. But as we will see, you can build convolutional neural networks that have some of the inductive biases of transformers, which is, for instance, they use the same type of normalization, they use the same type of activations, and they distribute them through the network similarly. And you can bridge the gap in robustness just by applying these inductive biases without ever touching the self-attention. So that's why these experiments are a bit inconclusive to support the statement. Also, there is no theoretical proof about the fact that self-attention is supposed to produce more robust features or better representations. So these statements that are reported in these papers are a bit hand-wavy. Also in this paper, they also say the fact that transformers seem to have better calibration might hasten the end of the convolutional era. So people tend to be very dramatic about it. For this reason,
I remember this paper. Like, did they have the same training procedure for the? I think they compared to ResNext or ResNet compared to transformer networks, or did they have different training procedures here?
I think they had different training procedures. Okay. If I'm not wrong, they took off-the-shelf models. They didn't retrain that.
Okay, but they had this interesting analysis also where they scaled the models, right? I think there was this paper, right, where they basically had a look at how the calibration changes when you scale the model, and then they saw somehow that calibration gets better the larger your model is, right?
Yes, which is a sort of trend that contradicts previous literature, because previously it was vaguely said, at least in the very famous Guo paper about temperature scaling and calibration, the one that everyone cites, they said, oh, okay, over-parameterized networks tend to have worse calibration, while their observation is the opposite in modern architecture. So over-parameterization is a bit vague.
Yeah, I think in their defense, maybe, I think they only look at the regime where you have a lot of data. So yeah, you could basically still, even though your model is large, you can still say maybe your data is infinite compared to your model parameters.
Yeah, actually, we will have also a quite long discussion about how to measure the capacity of your model, whether it makes sense to count the parameters of a model. So yeah, there is a lot to talk about in the paper. Okay, I think these few papers, I will just mention about this other paper, Transformers are Robust Learners. There are 2 points. One is about natural adversarial examples. I don't know whether you know this dataset, but there is this covariate shift dataset called ImageNet A, and Hendricks sort of reports that transformers do much better on this dataset. The big problem is also that this dataset was built by collecting samples that were misclassified by a ResNet 50. So anything that looks like a ResNet 50 is going to perform pretty badly on them. There is a strong bias against this. And we will show also a small fix that can help boosting the performance by a large amount. And also there are some methodological problems in the way out-of-distribution detection on ImageNet is performed, but we will discuss this when we will talk about our paper in particular. Now we want to answer the question, are transformers more robust and reliable of CNNs? Is this because of self-attention? So what do? First of all, we try to establish what it means to make a fair comparison between different architectures. We explore whether self-attention allows models to learn better representations, and we do so by checking whether transformers can pick spurious features and whether they are vulnerable to known biases. And in particular, we check 3 kinds of biases: the simplicity bias, the texture bias, and the background bias. And then we perform very classic evaluations on ImageNet scale, checking auto distribution detection, calibration and misclassification detection, and we also check generalization under covariate shifts. Of course, we don't claim much novelty on it because ConvNext had already made many of these evaluations for covariate shifts, but we sort of discuss everything in the context. So what are the problems with the literature we just mentioned? Many times the training procedures are changed. So sometimes the training procedures of CNNs are applied to transformers or vice versa. And this makes so that the comparisons can be unfair because, of course, if you're making a category of models underperform with respect to the other, you're not really being particularly fair. Some papers perform comparisons based on the parameter count, which is questionable in the sense that I can understand it sort of measures the efficiency with which the model uses its parameters. But still, there can be massive models with a huge number of parameters, and they still can have worse classification accuracy, even in in-domain test sets. So it is a bit questionable. Also, we will have some arguments about why parameter count should not be used for picking pairs to compare models. Also, these papers try to come to a very simple, sharp conclusion. Transformers are more robust. Self-attention makes models more robust. We would like to be a bit more cautious about this kind of statements. And we also show that just having better convolutional architectures can change completely this kind of statements. So first of all, let's understand what we mean by fair comparison. We assume access to the same pre-training data and fine-tuning on the same data sets. In some papers, they compare models that haven't been pre-trained on ImageNet 21K with models that have been pre-trained on ImageNet 21K. In the appendix, we show some numbers of models with pre-training and without pre-training, and pre-training can have a huge impact on the calibration, on the auto distribution detection. So it's extremely important to make sure that all the models you compare have been pre-trained the same way. We also do not swap training procedures between families of models. We assume that the proposed training procedure of state-of-the-art models is the best for that category. So we just pick the models trained at their best. We don't tweak their training procedure. We don't compare based on parameter count. So we just list all the models of a family. We don't care about how many parameters they have. And we perform the analysis by having a very careful look at all the metrics and all the evaluation setups to understand whether there might be something off in some cases. And as we will see, there is sometimes something off. So let's now discuss why comparing based on parameter count doesn't make sense. First, from a practical...
Actually, I would have one question.
Yeah.
So just to be sure about the settings, so here you mentioned pre-training and fine-tuning. So pre-training, so could you explain a bit more what is the training procedure, the full training procedure? So
okay, the pre-training is typically performed on ImageNet 21K, and the fine-tuning is usually performed. Yeah.
Yes, go ahead. I was just wondering if there is some training phase, because usually fine-tuning sounds like after training and pre-training sounds before training. So I was wondering if there is some middle step, but it's probably just you train the model, freeze the weights, I guess, and then you can fine-tune later on, right?
Okay, let me be more specific.
Yeah.
You always train all the model in this case. The fine-tuning is not linear probing. It's not like you freeze part of the model and then you fine-tune the head. In this case, you're fine-tuning the whole network again. So what they do is they pre-train on ImageNet 21K, then they take the whole model they have pre-trained on ImageNet 21K and they keep training it, but this time they chop off the head so that it has no more 21K classes, and they give it another, they initialize it randomly, and then they fine-tune everything from scratch, from the pre-trained checkpoints. That's the idea. Does it make sense?
And so the fine-tuning, what is the fine-tuning data set in this case? So you train multiple ones?
Sorry.
So sorry, I guess it froze. So the fine-tuning.
I can't hear you.
Does it work now?
I can hear both of you.
Okay. So my question was mostly, mostly like the fine-tuning data set. What were the fine-tuning data sets that you consider?
In this case, we only care about ImageNet 1K. Okay. The reason we had done some preliminary studies also on Cepher 10, Cepher 100. So we tried to add another step of fine tuning, but honestly, there were so many hyperparameters involved and you could decide on so many things. We had found some results that contradicted some papers about fine tuning, but then there were so many caveats to everything that we decided, okay, let's keep it simple, especially because we would need an even higher amount of resources to make sure that everything is done in a fair way. So let's focus on something that is limited in scope.
Makes sense.
But yeah.
Maybe one more question, but if you still talk about it, just feel free to skip it. So what are some like differences in pre-training when you compare transformers to CNNs? Like you hear a lot about transformers being pre-trained, also using self-supervised tasks on like gigantic data sets. I don't know, like maybe you can have a comment on that if you don't do that later anyway.
Okay, pre-training, self-supervised pre-training is definitely something very different from supervised pre-training. In a sense, there is also a nice work under submission at a conference from Amartya that is also at ETH, and they observe that self-supervised features have very different properties, especially when there are data sets with biases or where data sets have spurious features. So self-supervision can really make a difference in the quality of the features extracted. In particular, it is quite well known that supervised learning specifically can make so that a classifier can pick spurious features, because obviously if the only kind of supervision you receive is a class label and there is a spurious correlation between some features and the label, the classifier, at least neural networks, tend to focus on the simplest feature. And so having self-supervision prevents you from doing that. And this helps in settings where there are these kinds of problems. There are spurious features or there are biases in the data sets. So you can do self-supervised pre-training for both transformers and convolutional neural networks. We didn't consider those pre-training procedures as they weren't the most popular at the time the paper was written, but definitely you can do it and you will observe very different performance with respect to the supervised training ones. Okay, if this answers your question, I will move on. This is a point we make in the appendix, but it is sort of important to bring this up. First of all, comparing models based on parameter counts has limited sense, probably makes no sense, it's a bit strong, because when a practitioner needs to choose which model to use, there are several constraints. It's not just about memory constraints, there are also latency constraints, energy constraints, and also within the same family of models, models that have more parameters not necessarily do better than models that have less parameters. So we don't see why it should make sense to compare models across families when this metric doesn't even represent the generalization capabilities of a model within the same family. For instance, if you consider VITL, there are variants that use patches of 16 pixels and variants that use patches of 32 pixels. And you can see that VITL 16 has a much higher requirement in terms of computation. but it has 2 million parameters less, while VITL32 has 2 million parameters more, but it is much less intensive in terms of computation. However, VITL32 is much less robust and reliable than VITL16. So we cannot simply reduce everything to counting the number of parameters. Another point we make is that we want to understand whether self-attention is the component that makes transformers more robust. What do? We don't provide theoretical proofs about it, but we look into whether models that only employ self-attention without having convolutional components can pick spurious correlations. If we find out that they can, then probably they're not learning better features as it is stated. They still fail in the same way. At ECCV, we often receive this comment, oh, isn't this trivial because this is statistical learning, it's not causal learning. Yes, I sort of think it is trivial, but literature has had this trend of ignoring this. But maybe we can discuss later on about whether statistical or causal learning should be considered when talking about architecture. Now, we perform some experiments.
I might have one question. Yeah. So I think 2 slides before you mentioned that we should not base the evaluation on number of parameters, but then you mentioned also the number of flops, right? And I was wondering if this would be a better way to compare like models if parameters are not the right way to go.
No, the point is, okay, it depends on what you care about, in the sense that if you are truly interested into flops, then probably you would rather have a mobile net with respect to a transformer because it's going to be much more efficient. That's why it's a bit hard to come up with an absolute measure of what you want. You need to understand what are your constraints, and based on your constraints, decide what to do. Probably you would like to have the fantastic performance of the most recent model, but sometimes you just don't have the energy, or you don't just have the computational capabilities on your embedded device, for instance. So saying in absolute, this is the right number of flops, or this is the right number of parameters to do something is a bit difficult. That's why.
Makes sense. Okay, thanks.
Okay. So returning back to the biases we check the simplicity bias. I don't know how many of you are familiar with the simplicity bias, but the idea is that there was a paper some time ago in which they stated that stochastic gradient descent, when applied to neural networks, in particular convolutional neural networks, was biased to pick simple features with respect to complex features. Now, the definition of what is a simple feature or a complex feature is obviously questionable, and it is a bit vague and hand-wavy. But for practical concerns, let's consider these experiments. These experiments consider the simple feature to be the MNIST part of an image, while the complex feature is considered to be the cipher part of an image. From an intuitive perspective, obviously, we expect to have less variety in the MNIST part of the image, while we expect to have a larger variety in the cipher part of the image, because MNIST is made by digits, and digit shapes more or less are all the same, while for the cipher part of the image, yes, objects of a same class tend to have more or less the same appearance, but still there is a much higher degree of variability. From this point of view, I think one can quantify the complexity by just doing, I don't know, a PCA on the models and then checking the ratio of the variance explained by a certain number of components. But we don't really care about how you define what's simple and what's complex. What we care about is that many times transformers are argued to have the ability to look at the full image at every layer, at every stage, so that they can capture long-term correlations. Long-term comes, of course, from the NLP literature. And for this reason, they're supposed to produce better features. Then what we do is to do this simple experiment. We take an MNIST digit and we take a cipher image. We create this association, that is, the MNIST digit is 0, the cipher image is a car, or the MNIST digit is 1 and the cipher image is a truck. Then at training time, then we associate the first two to the class -1, the second two to the class 1, and then train a model. Actually, we fine-tune a model. Then at test time, what we do is we perturb either the MNIST part of the image or the cipher part of the image. By perturbing, we mean literally swapping that part with another sample in the MNIST dataset or the cipher dataset. Now, what happens is that if you perturb the MNIST part of the image, then the prediction of your classifier becomes random. Instead, if you perturb the cipher part of the image, the prediction of your classifier doesn't change much. Which is basically telling you that the classifier is not relying at all on the cipher part of the image, it's only focusing on the MNIST part of the image. This is known for CNNs. Then we said, okay, if transformers can really leverage the whole image to make their classification, then they should be able to recover from this kind of failure. They should be able to leverage the whole image. No, they tend to focus also on the simplest part of the image. In particular, at the bottom of this slide, you can see we do some visualization on the test set. On the test set, we can also flip the high part or the low part of an image. And in particular, you can see that the self-attention maps of the last layer, which are represented in the first and the second column, tend to cancel the complex part of the image and tend to focus mostly on the simple part. On the right side of this slide, instead, what we do is we present what happens when you pass through the layers of a transformer. And in particular, in the earliest layer of the transformer, you get some weird, almost random attention map. While the more you progress through the layers of the transformer, the more the transformer tends to focus on the simplest feature. So it is self-attention. Having self-attention is definitely not enough to avoid the simplicity bias, which means it's not enough to avoid relying on these simple but discriminative features that might be spurious. Another experiment we do is measuring the reliance.
So in that sense, the simplicity bias is just a feature of SGD, or like gradient-based learning.
Honestly, although that paper is about SGD, I think it's not really about SGD itself. Probably if you do it with ADAM or whatever it is, you're going to find the same.
I mean, or just backpropagation.
I don't think it's even backpropagation. I think it's the difference between statistical learning and causal learning, because in statistical learning, you care about correlations, and the networks, for some reason, tend to pick the simplest features. It would be interesting to have something like a small workshop paper saying, hey, it's not just SGD. Probably I should have wasted some time to do it because somehow that paper uses SGD because on that they show some properties, but probably you can also do it with any other optimizer.
There might be a simple explanation, or this might not be an explanation, but hasn't it been shown that neural networks tend to be biased towards low frequencies? So they learn those first. And then if the simple part of this is the 0, I mean, it has a lot less high frequencies than compared to the cipher part. So it makes a lot of sense that it first just converges to this kind of.
Yeah, actually, we had, while we were working on this paper, we were considering also that kind of experiments, low frequency, high frequency. Actually, the kind of spurious feature induced in this paper is also about frequencies, because they induce noises at different frequencies. It's definitely interesting. We didn't follow up on this direction, but there are other papers on another field, which is single multi-domain generalization, that actually argue that low frequency features contain information about the causal component of an image, while high frequency features are supposed to collect information about the appearance, and they should be more unstable across several domains. And for this reason, you can manipulate those features without touching the low frequency ones. But it sort of contradicts the statement you made, which is actually the one of neural networks tend to focus on low frequency features, because if they focused on low frequency features and they were the causal ones, that generalize across domains, then it would be no problem having multi-domain generalization, right? So
yeah,
it is.
I guess it's also like this famous cow on the green grass is also a counterexample, since the green grass, I mean, if you like it, you can view it as just monocolor. And then this is a low frequency that is a very spurious correlation that will break your classifier.
Yeah, and actually, it is. I think probably this is something lacking in the literature at the moment. But the lack of a definition of what complex means and how this relates to the fact there is a spurious association that is quantifiable in terms of probability of co-occurrence of some variables is something that completely underexplored. I understand it's very difficult to do.
It would actually be interesting, like, to see whether you are just falling for low frequency spurious correlations, but you would be robust to high frequency spurious correlations, and vice versa.
Yeah, totally agreed.
Yeah. So maybe one thing. So regarding with the Yanis just said about like the optimization procedure, maybe in like for example, the model will first convert to some easy point, like to classify the meanest correct. Then the model will stick to that point, will not go to the ciphers report. I think so. One maybe simple experiment and rule out this like possibility is that first we pre-train the model to make it very, very accurate on cipher 10, and then we like train it on these samples with meanest and the cipher 10 stacked together, and then we see the model whether the model will like change to the optimization the minimum point to another minimum point which have the simplicity bias. Then this will be a cue that tell us whether the model will really prefer to the simple like components of the imager, or they just this is just an outcome of the easy optimization or the early stopping of the optimization.
Well, the models we take are pre-trained on ImageNet 21K, then fine-tuned on ImageNet 1K. So they're already in a state of optimization in which they definitely know which are the complex features, at least with respect to Cypher. So probably having an experiment exactly on Cypher would be interesting, as it completely disprove because of course, if you have already learned the features of Cypher, it means you're literally forgetting them or at least neglecting them. Later on. But I think already when you pre-train on ImageNet 1K, more or less it's giving a hint you can already forget everything, because when you pre-train on ImageNet 1K and then fine-tune on Cypher, usually you get something like 96% accuracy. But it is also true that probably the co-presence of a simple feature in this case might prevent it from looking at Cypher. While if you first pre-train on Cypher and then on MNIST, maybe on MNIST plus Cypher, maybe the things would be different. It is definitely an interesting idea.
Yeah, I see. Yeah, thank you.
Okay.
Maybe a last question. I was wondering, so here you mentioned this simplicity bias, but it looks like simple features might be more robust intuitively than complex features. So it's harder to somehow perturb like a simple features, which are, I don't know, might be present like at all location in the image, so to say, compared to complex features, which is, I don't know, just textures and simple perturbation. So I was wondering if in this case, this might say that actually both transformers and CNN are somehow robust or can be robust in some sense.
The problem is the outcomes razor, which is find the most simple explanation, has the following part that makes sense for all the data. Example, this is an example, actually, an experiment we have made for the CVPR submission. If you have the need to classify the gender of people from their faces, and you have a spurious correlation on the hair color, your classifier will start picking the hair color in order to make its prediction. And because it's the simplest feature it can pick, and then it will get the wrong thing. So simple doesn't necessarily mean explanatory, but it can be discriminative in a certain training environment, but it may not be the right simple feature. So you want to have the simplest explanation, but it must still cover the most of the data, let's say that.
Okay, I see, makes sense, thanks.
So we also do some experiments on the background bias, so how much the models tend to rely on the background. This is part of the background benchmark that you can find on GitHub. What they do is they create a data set where they take samples of different classes and they mix their backgrounds with those of other samples of the same class or other samples of another random class. As you can see, the example of this butterfly, obviously the branch and the blurred leaves background is sort of reasonable for a butterfly picture. However, the water background makes no sense. If a classifier tends to rely on the background, then the difference between the performance on this set of examples that we call mixed same, so samples with a background that is taken from the same class, and samples with a background that is taken at random from another class, so mixed random, should be high. Should be low, as low as possible, right? And we measure the background gap between these two kinds of sets, and we observe that convolutional models more or less perform as transformers, but most importantly, the most novel convolutional models, which are the convex, perform even better than transformers. So definitely the self-attention is not playing a role in this, or at least is not the key component to blame for the ability to rely on foreground or background features. Another experiment we do to check for spurious features is this style texture benchmark, in particular the Q-conflict stimuli benchmark. What they do is they take an image of a certain class, then they take an image of another class, and they use the image from the other class to perturb the texture of the first image. So imagine you have the photo of a cat, then you have the photo of the skin of an elephant, and then they apply style transfer in order to apply the features of the skin of an elephant on the cat. Then what they do is they define some metrics that indicates how much the classifier is relying on the texture in order to make its prediction. And in this case, as you can see from this table, convolutional models can be as good as transformers. In this case, we have VITL that has an extremely high value on this metric, which is pretty good, actually. But as you can see, the swing transformers or the VIT of smaller size compare similarly or worse to convolutional models. And our point here is self-attention the core component to not rely on textures? And in this case, definitely there are models that only leverage self-attention without having convolutional biases that do worse than convolutional models. So once we have finished doing this analysis, trying to understand which kinds of biases self-attention can pick, which are more or less the same convolutional models pick, we also do an in-depth analysis on standard benchmarks on ImageNet 1K. In particular, we do some analysis on out-of-distribution detection, and we find it is very important to consider how you evaluate it. In particular, the most popular benchmark for ImageNet out-of-distribution detection is ImageNet O. What is the problem with this benchmark? There are 2,000 examples from the out-of-distribution set, and there are 10,000 samples from the in-distribution set. This means that there is a heavy class imbalance between what is in distribution and out of distribution, and the AUPR metrics is extremely sensitive to some choices of the evaluation setup. In particular, if you choose to assign the in-distribution class to be 0 and the out-of-distribution class to be 1, you get the values that we report in this red column, which are the typical ones reported by the literature. And if you cancel out the convex part, you can see that there is a sort of huge gap between convolutional models, which are on the top part of the table, and transformer models that are at the bottom part of the table. In particular, there is a gap of about 20% between the strongest convolutional model and the strongest VIT model. However, if you just flip the choice of the positive class, and so you look at this table, can you see my mouse? Yeah, if you look at this table, the gap is only of 1%. So it is pretty problematic to use the AUPR to understand how good a model is for auto-distribution detection when you have this huge imbalance between classes. In the appendix of the paper, we have an argument about why the OROC instead is stable across all the evaluation choices. We give a proof sketch. We didn't frame it as a proof because we thought it was sort of trivial and we didn't want to claim novelty for it. But there are all the mathematical steps to prove it. The OROC is stable across all possible choices of the evaluation, in particular, whether you choose the positive or the negative class, or whether you have data imbalance in the setting of auto-distribution detection. And in particular, if you look at the OROC column, you can see that transformers and CNNs, especially when you consider ConvNeXt as the competing architecture, have more or less the same type of performance. In particular, we also do experiments rebalancing the number of samples. So what we do is we resample the auto-distribution set so that we can balance the amount of in-distribution and out-of-distribution, and the AUPR can change widely when you perform this operation, while the OROC remains completely stable. The AUPR is sort of making an assumption about whether it is more important to confuse an in-distribution sample with an out-of-distribution sample, or vice versa, depending on which choice of the positive class you make, while the OROC is not making this assumption. So in case you want to make that assumption, AUPR is good, but you should be aware about which class you define to be the positive class. If you don't make that assumption, OROC is probably the way to go in order to make a fair comparison. Now, we also performed several experiments on calibration and on distribution shift accuracy. In particular, what we observe is we confirm the results observed by the authors of ConvNeXt. Probably I should have mentioned more clearly, ConvNeXt is this set of new convolutional architecture, fully convolutional architectures that bring in the convolutional architecture design some inductive biases of transformers, as I already mentioned, the normalizations, the activations, how they're distributed through the network, what are the proportions of the sizes of the layers, and this kind of things. And they managed to completely bridge the gap with transformers on the accuracy, both on in-distribution and under covariate shift. We test, probably there are a couple of data sets they didn't consider in the original ConvNeXt paper, but more or less we don't claim any novelty about this. They already checked this. ConvNeXt are more robust than the VITs or the swing transformers they compare against. But what we look at is also the calibration. And as we can see, the results about calibration are pretty mixed, in the sense that it is not possible to find a single model that is better than any other model in all the circumstances. So it is very difficult to identify a winner. And if it is difficult to identify a winner, it is also difficult to identify a winner between the two families. In particular, we also have a point about whether we should look at the calibration metrics and whether it is enough to check the calibration metrics, because if you think about it, the calibration metrics give you information about how frequent is the meaning of the probability you get out of the softmax, in the sense that if your model predicts 80% confidence, then you want to be accurate 80% of the times. Okay, but then what would you do with a model with a certain prediction at a certain conference? It is not sort of operational. You cannot just discard samples based on the confidence. Then we suggest it is extremely important not only to check for the calibration, but also to check for the misclassification detection performance. In particular, we use a metric that is the PRR metric. How is it measured? Very simply, you take all the samples in the test sets, you take the softmax, you take a confidence or uncertainty metric on the softmax, and then you sort them by decreasing uncertainty, and then you start rejecting these samples. One problem of most misclassification detection metrics is that they tend to favor models that have high accuracy. So if you are comparing two models and these have a delta in accuracy, the model that has higher accuracy generally will win. We use this PRR metric exactly because we want to factor out this problem. And this metric was designed specifically for that, because it takes an oracle, which quantifies how well the model would do if it perfectly knew which are the wrong samples, which is this blue image. So on the x-axis, you have the percentage of samples rejected by the oracle. You reject samples based on the decreasing order of uncertainty. Then you take your classification error on the set of samples you don't reject. And as you can see, obviously, if you perfectly know which are the wrong samples, your accuracy will, your error will decrease linearly until it goes to 0, and then it will remain constant. Instead, what happens in practice when you use a real model, you get this orange curve or something a bit more wiggly. This is probably just a toy example they made in the paper in which they proposed this metric. And what you do is you compare the ability of the oracle on a certain model that has a certain base classification error with the effective ability of using uncertainty in order to reject samples. And what you do is you measure the area under the random predictor. The random predictor is this dashed line for the oracle and for the model. And then they take the ratio of the area of the orange area with respect to the blue area. Now, one important aspect of this metric and the reason why we're using it is that if it is negative, it means that you start rejecting samples with higher uncertainty, with low uncertainty before the ones of high uncertainty. So, if it is negative, you're rejecting first the samples that are correct and then the samples that are incorrect, which means that you're assigning higher confidence to wrong samples. On the other hand, if it is positive, then you're assigning lower confidence to the wrong samples. If it is 1, you're doing the perfect prediction, so you're always rejecting the wrong samples. If it is -1, you're doing the complete opposite choice, so you only reject samples that are correct. Now, as we can see, sometimes it happens that these metrics can be negative. We have conflicting the results with the calibration, because if you look at the calibration tables, we have very low calibration error. While you can observe that sometimes the PRR is negative. So it means that the distribution of the confidences can be not only just having an overlapping part between the correctly classified and the wrongly classified, but you can also have the correctly classified ones to be assigned significantly lower confidence with respect to the correctly classified ones. In particular, we observe that, again, there is no clear pattern. There is no single model that outperforms all the other. And it is important to pay attention to the fact that PRR can be negative. So the takeaways of our work, I would say, are, first of all, self-attention is not enough to avoid biases. Self-attention doesn't do magic. It doesn't prevent you from picking spurious patterns. It doesn't prevent you from picking leveraging textures instead of shapes. It doesn't prevent you from leveraging backgrounds instead of the foreground objects. And one should be really careful when doing this kind of analysis, because transformers are not just made by self-attention. There are so many architecture design and training procedure choices, and accounting for all of them is extremely difficult, especially because the trainability of model is different based on different inductive biases. So we should at least be very cautious about what's being said when we try to identify the reason why a model is more robust than the others. We also show that transformer design has brought some novelties in the design of networks, and these novelties can be transferred to convolutional architectures as well. So maybe it's not a matter of convolutionally inductive biases versus self-attention biases. It might be, as we already extensively discussed, more of a matter of learning statistical correlations or causal relations between variables. In the appendix of the paper, we also have a quite long discussion about ImageNet A. As I already mentioned, ImageNet A has been collected adversarially with respect to a ResNet 50. So anything that even just resembles a ResNet 50 will perform very badly on it. However, we have observed in our experiments that if you do some pre-processing of the images, so you just rescale them, you're gonna have a huge jump in accuracy. So that benchmark should be used very carefully when doing comparisons. Another long part of the appendix is about the complexity measures, because we have just said, okay, choosing the parameter count is not really representative of the capacity of your model. It is true, but do we have any better alternative with respect to parameter count? And then what we do is we start looking at complexity measures that have been proposed in the literature to understand whether those complexity measures can do better in describing the capacity. And sadly, what we found out is that it is completely impossible to compare families of models based on those metrics, because they don't do better than parameter count at all. So this is an open area of research, but there hasn't been much progress with respect to what parameter count comparisons can do. And we also report some results with pre-training or without pre-training on ImageNet 21K, and we observe it is extremely important, especially when you do out-of-distribution detection. So this is the end of my presentation. If you have any questions, of course, you can make them. And
I would have one question.
Yeah.
Thanks a lot for the talk. So one question is, you mentioned in the bonus nuggets in the previous slide, so you look at other complexity measures. So what other complexity measures did you look at in the appendix?
We basically look at the path norm. I don't know whether you've ever heard of it. Or Frobenius norms of the weights. There are a series of papers that try to find generalization bounds for neural networks, theoretical bounds. And what they do is they try to make these bounds tighter and tighter. And these bounds many times depend on some features of the network, which can be the Frobenius norm of the parameters of the network, or it can be the path norm. If I'm not wrong, the path norm should be I don't remember well, but it should be the output of the network when you pass inside a matrix all made by ones, and then you perturb the weights of the neural network. There is a theoretical discussion in all these papers discussing why these metrics should be representative of the generalization ability of models. But we observe that these models are not, these metrics are not really effective, at least in practice, to make comparisons.
Okay, makes sense. That's very interesting. So another question that I would have is, in this paper, did you also look at adversarial robustness? Yeah.
We didn't look into adversarial robustness because one is not really my area of expertise. Two, we did a couple of experiments and it would have extended further the scope of the analysis. There are some papers claiming that transformers are more robust to adversarial attacks, but we didn't dig much into it, honestly.
Would you expect like some of these conclusions to extend naturally to also adversarial examples, or?
There is a paper from our lab about a training procedure that introduces a generative component in the process. So the idea is you introduce this pretext task where you have two parts of an image. You take two patches and these patches partially overlap. Then if in the training procedure of a classifier, you insert this generative component in which, given a patch of the image, you want to predict the other one, you observe that the robustness is much, much better. And this happens independently of whether it's transformers or ResNets. So I don't really think it's about the architecture design again. It might be that some types of attacks are relevant, because obviously if you have patch-based attacks, transformers have an inductive bias about processing patches. And so if you try to swap them, probably it will be hard. But I don't think for all types of attacks you can come up. Probably they have different transferability, so you cannot transfer some types of attacks from one architecture to the other. But I wouldn't expect them to be impossible to attack or more robust from that point of view.
Makes sense. Yeah, thanks a lot.
Yeah, maybe one more question. Maybe I missed it. What's the what are the inductive biases that ConfNext makes use of, or like the inductive biases then that are actually useful in transformers?
They actually have a very nice plot in their paper where they do all the steps they do passing from a original ResNet to a transformer-based like ConfNext. The most prominent one is, instead of applying ReLUs, they apply GLUs. Instead of using batch normalization, if I'm not wrong, they apply layer normalization. And they use a proportion of the blocks that is different. They train for more epochs because usually the base training procedure for ResNets was 100 epochs, while the one for transformers was 300 epochs. They also, if I'm not wrong, they also changed the optimizers. They use much less normalizations, because in ResNets you have a very frequent usage of batch normalization across the architecture, while transformers sort of use it more sparsely, the normalization, and so they also reduce the frequency of the presence of normalization. There should be another couple of tricks I cannot recall, but these are the most prominent ones I can remember. Oh, they increase the kernel size in the first layers, trying to simulate the patch-based, the ability of transformers to look at patches rather than small areas. Probably there are others, but if you go in the Convex paper, there is a full list of all of these inductive biases.
Okay, in your experience, do you think, so like while you said it's difficult to draw a conclusion from the quantitative experiments that you had, there was still some pattern in the sense that some architecture was really bad, like the BIT. Do you think like that these inductive biases that you concluded from Convex, or that were in the Convex paper, are actually something that is really useful? I mean, is this something that so the tendency that you also saw in the experiments, or because I don't know what the BIT architecture is, to be honest.
Yeah, the BIT architecture is a variant of ResNet 50. I mean, there are various types, ResNet 50, 100, 150,
yeah,
but there are not huge, massive differences with respect to a ResNet. They just pre-train on ImageNet 21K
okay,
and fine-tune on ImageNet 1K. When you see the multiplier, they increase the depth of the components of the convolutional kernels, but they don't really change too much.
So they don't have these inductive biases?
No, they don't have them. Convex instead still starts from a ResNet 50 architecture, but then if you read the paper, they show all the steps they do. So they remove something, they add something, and they see how the performance changes as you progress through the transformation to Convex. And as you can see from this table, for instance, the BIT architecture has something like 15% ECE on the ImageNet R, for instance, while the Convex architecture has 2% ECE, more or less 2% 57, the base model. So you can see there is a huge difference, and this is obtained just by changing those inductive biases. We had actually considered doing a variant of this paper, or we had considered asking for checkpoints, because in the Convex paper, they do an ablation for all the components they touch. And we sort of wanted to do that ablation also for measuring the ECE and other metrics, but we hadn't time for the submission. We asked the checkpoints to the people that developed Convex, but they answered but didn't provide them. And so we couldn't just do it. Also, we didn't have enough computational resources to train all the possible ablations ourselves. Because you had to pre-train on ImageNet 21K and then fine-tune on ImageNet 1K. It was a bit too expensive, but it would be really interesting to understand how every of these inductive biases have an effect on the uncertainty.
I see. And between like VIT and SWIN both have these inductive biases, right?
I cannot tell too much about SWIN, because I think the most prominent difference between SWIN and BIT is the fact that they have SWIN induces some convolution-like bias, in the sense that instead of taking a grid of patches, it allows for the patches in the input image to overlap partially, a bit like a sliding window. Indeed, SWIN means sliding window. And this has been observed to improve the performance of transformers. And it still has the self-attention, and it still has all the associated things. So if I'm not wrong, it doesn't change too much in the structure, because all the transformer architectures, most of them at least, have been developed with the goal of reducing the training complexity, because VIT, the original paper, could only be pre-trained on ImageNet 1K and fine-tuned, ImageNet 21K and fine-tuned on ImageNet 1K, because if you trained it from scratch on ImageNet 1K, you wouldn't be able to compete with convolutional models. And most of the papers were like, oh yeah, let's try to find a way to train transformers, but directly on ImageNet 1K. And then thousands and thousands of variants of VIT came out. And they all more or less tried to do something that resembled convolutions, because it was believed that in convolutional inductive bias somehow facilitated the training, but still introduced those bad biases we talked about. So,
okay.
yes.
Cool, thank you.
Hey, maybe one question is that, so regarding on the table, like PRRs, like performance, so it is a bit like expected that so some very little change in the network will have a lot difference in the PRR metrics, like for the BIT, which was net 101, then so very like poor performance on the PRR calibration. And or so regarding that, do you think something like random seed will have a large impact on the robustness evaluation based on your like experiences on that?
Yeah, this is actually a big problem of the literature of these foundational models. Since academic researchers don't have the resources to do multi-seed experiments, they tend to leverage pre-trained models that download from the web, as we did too. And so we only have access to one seed. And it is difficult to assess whether that seed was lucky or unlucky. For instance, we are using the team library checkpoints for these experiments, and the VIT large model of this library is extremely strong. It's way stronger even than the model, the numbers that were reported in the original VIT paper. We don't know why. We don't know whether it's a lucky seed. We don't know whether they did something weird in the training. We don't have access to this kind of stuff. And probably in order to make this kind of literature more reliable, it would be necessary for those who release the models to provide not only one seed, but multiple seeds, and not just their best seed, let's say that, because we know how research goes.
Yeah, right. Yeah, so this sounds like very interesting to the robustness evaluation part, because like these seeds will have like not that large impact on the accuracy side. So they have some impact, but that will be not that large, and also they will have very large impact on the if you take focus on the calibration. I mean, so this will like have some like interesting maybe application afterwards. So can we also just by like randomly choosing some models and then pick the one which actually calibrate well, calibrate the most, because this randomness will have larger impact on the calibration. Yeah, but I mean, so this is not relevant about so this paper, but just one single idea. Yeah.
No, and the interesting thing is that at least a good trend I've observed in the architecture design literature is that somehow, since the performance on ImageNet is saturated, they started doing analysis on ImageNet AR sketches, so that if their performance improves on them, they can still sell the paper and get it accepted. And it has become more frequent to check for the calibration, but still it's not as widespread as it should be. And similarly, all other downstream tasks. It is also true that now that large language vision models are coming out and the trend is shifting, things might change again. But yeah, I feel it's important to start checking for metrics and for evaluation setups that are not just a classic accuracy evaluation for more recent research.
Yes, agreed. Yes, thank you.
Cool. Yeah. Then thanks a lot for the presentation, Francesco.
Thank you for inviting me.
It was a pleasure. I love how Bertrand is using the reaction smiley all the time.
Well, I cannot even see them probably because I have collapsed everything.